Okay, so we're going to look at, we're slowly building up the sophistication of the problems. So if we look at what we have here, rather than having a string of impulses, which probably doesn't happen all that often in the real world, but look at our input here. This is a step up and a step down. Basically, this is flip a light switch on, flip a light switch off. The reality is people turn machines on and turn them off all the time. So we have a very realistic input right here. So and in this case, the input is at 0, and when we turn it on, it goes up to a half. It lasts for 1 second. It turns off. So there. But this type of input, where something switches on and switches off later, totally realistic. Here's our impulse response. I've never seen anything that would do this. In the world of digital systems, this could be done. Relative to the real world with physical systems, yeah, it won't happen. But we're just slowly building up our sophistication. So here I'm having an impulse response that when it gets hit by an impulse, what does it go up to? I don't have it listed here. 1. This goes up to height 1. All right. So at time 0, when the impulse happens, or the input happens, if I said that wrong, if it were to be hit by an impulse at time 0, it will jump up to 1, and it will last for 2 seconds, and then it just instantly falls off, and then it's all 0 again. All right. And here is our, just for reference, our convolution equation. Integrate from 0 to t, where t is the time that you care about to solve for. I of t minus tau, s of tau, d of tau. There we have it. All right. So to do problems like this, this problem is going to start to show where the integral can be very helpful. So let's look at time equal to 1/2. So I take this. So here we are. Input starts at 0. We flip it, and at t equal to 1/2, we slide it over 1/2 second. So first thing you do in these problems is draw the picture. So at t equal to 1/2, here's the front edge of the input at 1/2 of a second. The input goes back for 1 second. So at minus 1/2, here's the back end of the input. This part hasn't excited the system yet. This part is, and you're seeing here's the front input exciting it here, then this is exciting that, and this is exciting, so on and so forth. Okay, this integral says flip and slide the input to the point you want. In this case, 1/2. We did that. Then these two parts say multiply it together. So if I multiply this by this, and I don't have impulses now with their weird sifting rules, we just normal multiplication. There is no impulse response out here. There is input. So and when we multiply them together, we get nothing. Okay, here's the input's 1/2. The response is 1. If I multiply 1/2 by 1, I get 1/2. And it only goes out to time equal to 1/2. So all of this stuff does nothing. So what do I have? This goes up to 1/2. It'll last for 1/2. And then it says this is an integral. Take the area under the resulting curve. The area here is 1/4. Now, if you're doing this with this integral, what you'll notice here is that you have to be careful. You could actually do this in such a thing, and you could actually do this as a function of time, and you could let this front input, starting at 0, it could go to 1 second. Why do I say that? When this front edge hits 1 second, this back end will be hitting here. If we let our time go any farther, there's no more input to excite the initial part of the impulse response. So we're going to have an empty zone. All right. So whenever you basically have the corners of the inputs or the impulse response cross, we need to rewrite the equations. This is going to become more apparent here shortly. So let's just stay with our sort of a hand approach at time equal to 1/2. We flip the input, slide it to 1/2, multiply the impulse response times what is there in the input, take the area of the result. You get 1/4. All right. If we go to t equal to 1, all right, and here's what I was just talking about. Here's the first input. It slid 1 second in. So the back part of the here, the last input is now starting to excite this impulse response. All right. So now we look at that. We multiply them together. We have something that this is a half, this is 1. So we get 1/2 for 1 over 1 second. The area is 1/2. Okay. So now let's go to 1.5. And notice what happens. Here's the first input. This, what happened at 0, is now 3.5 seconds into the impulse response. What happened at 1 is only a half a second in. The intervals, so here I've now drawn my input, my impulse response. Now I multiply them together, and I get from 1/2 to 3/2 something with height 1/2. Area is 1/2, because that's 1 by a half. All right. Now, so once we get to 1.5, okay, we can continue. So if we let this go for another half a second, what's going to happen? You're still going to basically have the same. If you multiply this by wherever this is, you're still going to get your half. And so after 2 seconds, which is symmetrical with the 1, the front input comes out, so it's no longer exciting anything. And as we continue on to 3 seconds, the intersection of this and that will become 0, and so the response will be looking like this. From 0 to 1, it builds up to a half. From 1 to 2 seconds, we have this inside of this, so we're going to stay at an output of a half. And then, as it works its way out, the area will be shrinking, and it'll go down to 0. And if you look at it this way, if your impulse response lasts 2 seconds and your input lasts 1 second, it says after the last input at 1 second, the impulse response will last 2 seconds more. So the total response is 3 seconds. And we can see that right here. I'm going to end this video right here, and we're going to have a more sophisticated problem coming up next. See you soon.